nice kind presentation. So I'm going to start sharing the screen. Well, good afternoon, everybody. Like said sure, my name is Daniel Aguilera. I'm going to present the preliminary results of the production of aerogels using hyaluronic acid molecules. And well, let's start with the definition. What is hyaluronic acid? Hyaluronic acid is an ionic heteropolysaccharide. It is compounded by two kind of monomers, the glucuronic acid and the acetylglucosamine. These two monomers that compound disaccharide units inside of the hyaluronic acid have different functional groups that make this molecule, the hyaluronic acid, highly polar and very hydrophilic. The hyaluronic acid is also the main component of the extracellular matrix. The hyaluronic acid also have a very important function, physiological function, like a body lubricant is also important in the hydrodynamics of the tissue, the movement and proliferation of cells, and receptor helping in the cell receptors surface. All these characteristics make the hyaluronic acid biocompatible, and the fact that the hyaluronic acid is a natural polysaccharide is also biodegradable. All this feature, together with the fact that is commercially available for different sources like human, animal, or bacterial source, make the hyaluronic acid one of the most extended polysaccharide uses in biomedical application. The use range from ophthalmologic, rheumatologic, the most common is noted like in dermatologic for aesthetic and clinical medicine, but in my presentation, I'm going to focus more in the use of hyaluronic acid for wound healing. In fact, the hyaluronic acid itself in our bodies have many roles in the wound healing process. He can be present in all the steps of the wound healing process, from the formation of the clot, also helping from the synthesis of different connective tissue, etc. And in fact, in the level of commercial market, there are different products based off hyaluronic acid, products in the presentation of creams, gels. However, there are still missing development for chronic wounds. And this is important because in the context of the European Union, the population is aging, and for this situation, the prevalence of diabetic ulcer is frequent, and this make the production of chronic wounds. So for the chronic wounds, it's necessary a specific type of wound dressing. And this wound dressing have to be an ideal characteristic. For example, you see here in the slide, in the down part, these characteristics of an ideal wound are related with the type of material that you are using. It's necessary material that help to the production of connective tissue, keep the methionine and the wound site biocompatible. This is possible with the hyaluronic acid. However, there are other characteristics that are related with the way that you make the material, how to produce the material. And these characteristics are gas exchange in the wound site, exudate absorption, the release of therapeutic agent. And these characteristics can be also fulfilled by the aerogels. But what are aerogels? Aerogels is a solid polymer network that is mainly made by air. This is dry, ultralight, and the characteristic that is the most important for wound dressing is the fact that have high surface area and high loading capacity, and this is going to help to, for example, the exchange of oxygen, CO2, with the wound site, also help to the exudate absorption, and also this kind of formulation based of aerogel in comparison with formulation of creams, other type of membranes, these aerogel have a high loading capacity, helping to the release of therapeutic agent. So after this introduction, the idea of the project was make the preliminary evaluation to evaluate the possibility of produce hyaluronic acid aerogel. We will focus in try to find a methodology and the parameters for produce aerogels based only in hyaluronic acid. This is important because there are not previous reports of solely is mean using only hyaluronic acid for produce aerogels. In order to evaluate the condition for preparing hyaluronic acid aerogel, we started with two methodologies. Both methodologies without any chemical cross-linking. It means we're starting with the native hyaluronic acid. The first methodology was the non-solvent induced phase separation, and the second one was the freeze-thaw-induced gelation. For both methodology, we changed different parameters. For the first one, we modified the type of the solvent, ethanol acetone. We work with two different extreme concentration of hyaluronic acid, a low concentration, high concentration, and for pH, and for the second methodology, we work with two different concentrations. In total, we evaluated 18 precursors with this combination of parameters in order to see if it was possible to get aerogels. To characterize the material, we use the volume shrinkage, the density, the surface area, and the evaluation of the network morphology by CEMEF. This is also the order of the presentation of the results in this presentation. Let's go to talk in more detail of each one of the methodologies. The methodology of non-solvent induced phase separation started with the native hyaluronic acid with the different concentration, and then in a subsequent step of modification of the pH, we increase or decrease the pH of the solution, and then we transfer it to a mold. Then in this methodology, and this is the most important part of this methodology, we add a non-solvent. It means a solvent different than water. In our case, we use acetone and ethanol. This can promote the coagulation of the hyaluronic acid and eventually generate gelification and produce a precursor. We use to eliminate the solvent and get a dry material, in our case, the aerogels, the methodology of the supercritical drying using CO2. Well, for the second methodology, the freeze-thaw-induced gelation, many steps are shared with the previous methodology. We started with the hyaluronic acid, native one, two different concentrations, but we are going to have three different things with comparison with the other methodology. The first one, for this methodology, we are always work with acid pH. Then we are going to transfer the solution, and this is the key part, and that is the reason why it's called freeze-thaw-induced gelation. We are going to put the solution in a freeze, unfreeze, and do again this process in order to get hydrogels. Then we have to replace the water inside of the hydrogels to get alcohols. And with the ethanol inside, this is going to be soluble in the CO2. So we are going to be able to remove the solvent and get dry materials. So let's go to analyze the results of the project. We started with the evaluation of the volume shrinkage. Here in the slide, I'm going to present the result for the when this material was produced using ethanol like as on not solvent, lower concentration of hyaluronic acid, and for all the pH. For evaluate the volume shrinkage, we simply take the volume of the solution and then measure the volume of the final material, the dry material. For this result in ethanol and low concentration of hyaluronic acid, we observed that from the 4 pH, only 1 pH wasn't able to get the material. For the other, was possible to get a dry material, and in all the cases, the shrinkage was higher than 90%. If we compare these results with samples with higher concentration of hyaluronic acid, we get that was possible to get all the material to all the pH, and also we can see that the pH has an effect. A higher pH, we have less shrinkage of the material. Then if we compare the boot concentration, there are less shrinkage when we are using higher concentration of hyaluronic acid. Then if we compare in this methodology the use of ethanol versus the use of acetone as a non-solvent, basically we see a similar behavior, but both not solvent. Basically we have shrinkage higher than around 90%. And only in some cases, we observe more shrinkage when we are using acetone. However, if you see in general, we don't see a real trend by the use of the pH. We don't see a strong effect of the pH, more in the pH 12. However, the pH have a really important effect on the shape of the material. As you see here in the slide, when we modify the pH of the material, the shape completely changes. So it means that something is happening inside. Other fact that is important to highlight here is to evaluate if our methodology of drying is efficient. Why? Because we are having a strong shrinkage, but we want to know if it's at the end we are getting aerogel. So we compare this methodology of drying with eye drying, and if you see in the figure, the supercritical and drying methodology generate material with less shrinkage. However, until this point, we can be able to say if we get aerogels or no. For the reason we need other characterization techniques like density, surface area, RCM, and also we wanted to evaluate how is this methodology with the second methodology, the freeze-thaw-induced gelation. Let's start with the comparison of the methodologies. Here at the left, we have two materials that was produced with the non-solvent induced phase separation, and here in the right, under the same condition, but a different methodology, the freeze-thaw-induced gelation. With this methodology, if you observe here, we get bigger material with less volume shrinkage. So it means that the methodology have a real important effect of the size, shape, and volume of the final material. In order to go deeper of the difference of the condition and both methodology, we evaluate the density. In the slide you see for the first methodology, non-solvent induced phase separation, the differences between concentration, blue and red, different pH, and different non-solvent, ethanol and acetone. In general, we can say that we have material with low density, but we can observe that when we are using acetone, a solvent with lower porosity, for some materials, the density is higher. Also, with higher concentration, we are going to have higher density. This is obvious, more hyaluronic acid, more density. And here is more clear the effect of the pH. For example, with the acetone, when we are working with higher pH, the material is going to have more density. If we compare this methodology with the second methodology after freezing, only with the pH 1.5, we observe with the second methodology, we are having material with really low density. We're having really light materials. Now, we move to see the superficial, specific surface area. This is a very important test for us because at the end is the test that is going to tell us if we are getting aerogels or not. Why? Because by the definition, the aerogel have to have a surface area higher than 150 meters square per gram. And if you see here in the slides, we were able to have aerogels, but only working for the methodology of not solvent with a pH of 2.5. In fact, this pH is the isoelectric point of the hyaluronic acid. In the case of the second methodology, freezing the precursors, for both cases, we get aerogels with also nice and important surface area. So we wanted to confirm all these results, and for that, we do the evaluation of the network morphology using CEMEF. In this slide, we are comparing different parameters of the first methodology of synthesis. In the upper part is a solid that we are sure that is not an aerogel because the surface area is low, versus a material with a higher surface area, the one that was produced at pH 2.5. The first small conclusion here is, of course, the material that have low surface area have only macroporosity, only big porous, like here you see in the scale. But for the material with the higher surface area, we have only mesoporosity. So this is good. So it means that we are confirming that we get aerogel. Then if we move to see the second methodology, the freeze-thaw-induced gelation, in that case, we observe the formation of the mesoporosity, confirming the formation of the aerogel, but also this methodology generates a dual porosity. It means that we also have macroporosity, big porous. And also this means that the freeze-thaw methodology generates a hierarchical porosity and is related with the freezing steps. Well, in order to conclude, we can say that we were able to obtain aerogel based on hyaluronic acid using two different methodologies, and both methodologies without any cross-linking. And this material, after the analysis of the properties, have a potential use for root dressing, especially taking account the big surface area, allowing this material be an excellent candidate for make a drug loading, and also to evaluate the gas absorption to be applied in the wood site. It's more particular, like I said at the beginning of the objective, we started with 18 materials, and the conclusion was we get 6 materials that fulfill the requirement. They are aerogels with a nice density and high surface area. Well, in terms of the perspective, like I said at the beginning, this was a preliminary evaluation, so the perspectives are huge. So the first one is continue with the study more parameters in the second methodology, the freeze-thaw-induced gelation. We also are going to move to evaluate the mechanical properties of all the materials. I start to do the test for the drug delivery. Of course, we are focused these materials for the wound application. We need to do the biocompatibility evaluation, evaluate other type of material, introducing a cross-linking agent, and other applications, not only wood race. Well, I want to say thank you for the because this project was carried out in the frame of the Oligo project under the financial support of the French Agent National of the Research, and also thanks to Paris Band for the supercritical drawing and Suzanne Jacom for the same image. This project was developed in CEM, in the Center of Material Forming at Sophia Antipolis in France. And thank you for the attention.
Thank you very much, Daniel, for your interesting contribution. We have here some questions, and I will start it with the one related to the effect of pH on the shape. And the question is, if you have any explanation why changing the pH, we have different shapes and morphologies.
I want to put this. Yeah, exactly. There are two explanations, one macro and one micro explanation. The first is when you modify the pH in a hyaluronic acid, you also are changing the viscosity of the material. So when it's happening the coagulation, the mechanics of coagulation will be different if you have material with higher viscosity or lower viscosity. This is the first explanation. Second, microscopic level, when you change I'm going to put this slide, this another slide. When you modify the pH, you are, for example, you are going to decrease the pH. You are going to protonate the carboxylic group of the hyaluronic acid. It's make that the interactions, like hydrogen bind and other type of not covalent interaction, is going to change completely thanks to the pH, and this is going to see a repercussion in the shape at the end.
Okay, thank you for your clarification. And we have another question that is, do you expect that your aerogels dissolve in contact with the wound exudate?
Yes. Actually, we already make some preliminary tests of the solubility. The material are soluble. For that reason, in the perspective, we have to see what happened when we use a cross-linking agent. We decided to start with this methodology, even if they produce aerogel that are soluble, that is going to be soluble, because first we wanted to see the viability to produce aerogels, and second, the fact that it's soluble in the wound site is not itself a bad thing, like a starting point, because also we can see how is the profile of the drug release, but taking account the solubility. In the future, we want to add, like I said before, the cross-linking agent to produce gels that are not soluble in the wood seed and see how is the diffusion of a drug in the wood seed. So we have a starting point now to move to the second part of not soluble in the wood seed site. Sorry.
Okay, thank you. I also have a question because it was not clear for me why study only hyaluronic acid. I know it's interesting polysaccharide, but hyaluronic acid has been combined with different polymers and molecules for the application and wound healing. When using only hyaluronic, for example, we don't have antibacterial, antimicrobial properties that are important in some wounds clinical situations. Is there a problem, or what was the reason for choosing only hyaluronic acid?
Okay, well, there are two mainly reasons. The first one is because we want to use the only hyaluronic acid to make the drug release with an antibacterial agent. So we want to look at methodology to put the antibacterial agent inside. So for that reason, we said, okay, hyaluronic acid plus aerogels. So see if it's possible to put this in this network that offer the aerogels. The second is because, okay, these results are really preliminary. This is after 3 or 4 months of research. It's not really long, because this belongs to a bigger project. In the bigger project is consider they use the hyaluronic acid with the cross-linking agent. So at the end, all the idea is always use this material and put the antimicrobial agent inside.
Okay. So here you are more centered on the production and understanding how you can improve the properties of the aerogel, but then in the future you will consider also.
Exactly. Here is basically one question behind of this presentation. It's possible to get aerogels with only hyaluronic acid, because in the future we want to try different type of formulation of hyaluronic acid.
And now you can prepare.
Exactly.
You are in the good way.
Yeah, exactly.
So Danielle, thank you very much. Very interesting.